Okay, at least we wait for 1 or 2 minutes, then we'll start. Okay. Yes. Tell me more, Nikhil. Why? Yeah, that's what I'm telling. Most probably April, the first week of April, definitely all of you go to reported, I think, here. There's no doubt. Yes, yes. See, what about your area, ma? Now, I think most probably the corona cases are decreased almost. Yes. What about your places? Anyone?
Yes,
Sir,
sir,
fine.
mostly decreased.
Mostly decrease. Yes, yes. Okay, I think Tamil Nadu also almost decreases now. I think less than 500 per day. I think it will coming. Anyway, it will go at least 1 month. Mostly, the number of cases is further reduced per day, 100 or something only. I think almost reduced now. Okay, I think now we'll start. See, what about the last class? The previous class we discussed the instrumentation of ultraviolet visible spectroscopy. Okay, so that time I clearly explained about why you go to take that range, that UV visible range, that 200 to the 800 nanometer range, and what are the different components in that instrumentation. So, source, light source, what type of light source you are using, and chemical substance detector is nothing but a photodiode, then amplifier. Okay, and finally display devices, that is a normal CPU. Okay, now in this lecture, that lecture 15, that is a two part. First one is you go to measure, how you go to determine the band gap by using that UV visible spectroscopic data. From the data, how you go to take this band gap first. Second one is photoluminescence. So that is a repeated one. The photoluminescence is almost a repeated topic. That is a recombination and carrier generation process, radiative and non-radiative transition. Okay, but anyway, the first topic you go to measure or how you go to determine the band gap by using that ultraviolet and visible spectroscopy. Okay, that instrumentation already studied. So when the light is passing through the substance, for example, you go to take some samples or thin films, whatever. So definitely some amount of light energy is absorbed by the impurities or certain things present in that sample. So what much amount of that absorption takes place? Okay, you go to check, and there are two different formulas. Law already you discussed, that Beer laws and Lambert's law, and the combination also we discussed. So now by using that laws and the data, now you go to determine the band gap. Okay, see that valence band, conduction band, they are given. I think these things leave it that. Okay, valence band, and this is the conduction band. The energy gap is Eg. What about that energy gap? Only you go to find out with the help of the data. With the help of the data, you go to determine the band gap of different materials, semiconducting materials. Okay, especially the direct band gap or indirect band gap. Okay, whatever. Okay, see. So the band gap refers to the energy difference. I don't need to say. I think almost all of you know between the valence band and conduction band. Top of the valence band, bottom of the conduction band. And in order to take the electron jumping from valence band to conduction band, it requires some amount of energy that is given by the photons of energy actually or light. It's nothing but the photons. Okay, and the conditions already you know. what happens when E is greater than Eg, and what is less than E is less than Eg, which one is radiative transition, which one is non-radiative transition, everything already you discussed. And for energy gap, insulator is for that is greater than 4 eV, especially in the case of semiconductor, that is in between 0 to 3. Approximately, the semiconductor, the band gap is in between 0 to 3 electron volts. Okay, so they go to take that materials here, different materials, semiconductor materials such as gallium, aluminum arsenide, okay, indium, gallium and arsenide, so indium, aluminum arsenide. There are so many cases, and the reference one they go to take these materials here. So this is the article, the research article available. If you want to check, you go to check. This is the, they go to determine the band gap of different materials. Okay. Now, how you go to measure by using the data? That is based on the graph here. So now you go to draw the tau plot. I go to explain what is the meaning of that tau plot like that. See tau plot. By using this only, you go to determine the band gap of semiconductor, especially semiconducting materials. Okay, this is nothing but a graph between that energy. Before you move on to that formula I go to explain. Okay, see, the tau is the first man to identify the determination of optical band gap, where in 1966 here. This is the article. They get the article here published in 1966, and later that Davis and Motis further they go to develop, and also they go to find out the band gap of the amorphous germanium semiconductors. Okay, amorphous germanium semiconductors, and they go to show the relationship between, okay, that energy in this equation, the absorption as well as the energy. So my left hand side, you see here alpha h nu whole power 1 by n. So alpha is the absorption coefficient, h is Planck's constant, nu is the frequency of photon. That is equal to, or this is directly proportional to the energy difference between. Okay, so what is h nu here? What is h nu? Anyone? What is h nu more? Hey, what about this one, h nu here? Whether it is E or not. What is the E? Energy E is equal to h nu, and this is Eg is the energy gap. So that is E minus Eg. Okay, there are conditions are there. E is greater than or E is less than. So that h nu minus Eg is nothing but E minus Eg. So this alpha h nu whole power 1 by n is directly proportional to the energy difference. So that is E minus Eg, or that is equal to some constant. That the constant is A here. So A is the proportionality constant. That alpha h nu whole power 1 by n is equal to A h nu minus Eg. So the based on this equation only they go to draw the graph, and that h nu along the x-axis, that is energy along the x-axis, and this term, that alpha h nu absorption term along the y-axis, you go to draw the graph. So from the graph you go to identify the linearity of the graph. Now you go to identify the band gap, that is the band gap of particular material or semiconducting material. Okay, understand? See, say yes or no. Yes.
Yes, sir.
Yeah. See, this equation, that equation 1 gives the relation absorption as well as the energy difference here. Energy difference. So the plot is there. I go to show the plot. Before move on to that one, at least we go to see here. What is the conditions here? So there are two type of semiconductor is there. So what is the value of n? See that the exponent n is nothing but the nature of the electronic transition. So whether it is a direct band gap or indirect, or that is allowed or forbidden like that. So there are four conditions are there. When direct allowed means n is equal to 1 by 2. Whether that is a direct forbidden transition, n is equal to 3 by 2. See here, 1 by 2, 3 by 2 for direct, allowed and forbidden. Similarly for indirect, allowed and forbidden, that is n is equal to 2 into 3. Okay, now, for example, I go to take germanium. So what about germanium and silicon? Whether it is a direct band gap or indirect band gap? Yes, say anyone? What about your germanium and silicon? Whether it is a direct band gap semiconductor or indirect band gap semiconductor? Germanium and silicon. At least say one or two, yeah.
Direct.
Direct band gap. Atul, both are direct band gap. Yes.
Indirect band gap.
Indirect. Indirect. See, gallium is a direct band gap here. Germanium and silicon is an indirect band gap semiconductor. So, for example, I go to take germanium and silicon, we put the values here that 2 and 3 for allowed and forbidden. But in the case of we go to take the direct band gap semiconductors, we go to take this n equal to 1 by 2 and 3 by 2 like that. See, the allowed transition dominates the basic absorption process, and you go to give the values n is equal to 1 by 2 or 2 or like that, whatever for allowed transitions. So forbidden transition, you go to take 3 by 2 and 3 like that. Okay. So this plot, okay, you go to draw the plot, and now I go to show the plot here. For example, then only you go to understand something. See, so this is the tau plot here. See here, it's a tau plot, and along the x-axis, that energy is there. That is h nu. That is the energy of the photon. And here, in the y-axis, that alpha h nu whole square. That is absorption units are there. So this is absorption term. So the graph is like this. So this is the my example. I'm telling this is a zinc oxide thin film. This is a zinc oxide thin film. The reference is given here. Okay, that illustrate the method of fitting the linear region to evaluate the band gap at the x-axis intercept. So and the line go to intercept here. See here. How you go to draw the curve file like this? For example, I go to choose the zinc oxide thin film. I don't know what is the band gap, range of the band gap. See, the germanium silicon already some values are there, 0.6, 1.1 EV, 0.6 EV like that. But this is a zinc oxide thin film. I don't know what is the band gap. But anyway, that is in between 0 to 3 only. Okay. So that's why I slowly increases the energy. So example, see here in the graph, from 3, some nothing is happened here. There is no absorption. There is no absorption. So 3 up to 3.2, see here, almost nothing is happened here in that y-axis. That means the given energy, for example, that energy, that is a low photon energy. Low photon energy. So simply there is no absorption here, full and fully transparent. So that is transmission takes place. So there is no absorption. So that's why your curve is like this. You understand what I am telling or not? Please say yes or no. Yes, at least then only you know whether you understand.
Yes, sir.
Yeah, yeah. So now I see. I go to explain the graph here. See, first at low energy. See, the characteristic features of the tau plot is at low photons energy, the absorption approaches 0. That is, the material is fully transparent. So that's why it happened here. See, up to 3 to 3.2. See here in your graph, up to 3 to 3.2, and your absorption almost 0 here. See, nothing is happened. That means that material is full and fully transparent. Then further increasing that energy, okay, slowly, see here, the slowly, maybe after 3.21 or 2223 like that, okay, it will slowly increases. So, and slowly increases, something reached, for example, it almost 3.2, this is 3.22, 24, 26, 28 like that. So simply, the energy goes on increasing here, the curve is almost increases like this here, almost increases and reaches the maximum value here. Then you go to draw the tangential line, and they go to meet at x-axis here at this point. So this point you say that is the energy band gap for that particular material. So in the from the based on the graph, you say that is roughly 3.28 or 3.27 something. See here, this is the 3.27 they are mentioned here, 3.27 something they are mentioned. So that is a optical band gap of zinc oxide thin film. Zinc oxide thin film. See here, the reference 5 is given. The determination of thickness and optical constants of zinc oxide thin film prepared by the filter cathode vacuum or deposition method. So this article published where in 2008, and they identified that the value is order of 3.27. So the reference they are given here. Then the explanation is there. So why that is linearity is coming. So near the band gap value, the absorption slowly increases, gets stronger, and shows the region of the linearity in this squared exponent plot. So once the energy beyond the value, that is greater than Eg, so this linear region has been used to extrapolate the x-axis intercept to find the band gap value. That is 3.01. So what happened? Your E is greater than Eg, even at high energies, the absorption process saturated and the curve again deviates from the linear curve. That instead of linear, maybe it will deviate because now the E is far greater than Eg. So initially we do not know what is the energy gap. That's why that energy slowly increases. Okay, so when E is less than Eg, E is equal to Eg and E is greater than Eg. So like that you go to understand the curve. From this curve, at least you go to understand something here. Okay, so this is less than up to this 3.2122. After that only it's very close to the value, and that absorption increases. Almost they go to increases suddenly where from this point to this point. See here, almost it will increase suddenly. So that region only go to draw the line where they go to intersect in the x-axis. That is your band gap of that particular material. So here, the example they go to choose is zinc oxide thin film. So that value is 3.27. Are you understand? Say yes or no. Yes. See whether you understand or not.
Yes, sir.
Yes. Then how you go to justify this one? See, the justify the linear region for the extrapolation, one must understand the reason. So why for this lower as well as the upward deviations. When the low energy already I told, and that means there's no absorption. So the linearity can be associated with the defect absorption state and the near band edges. And the phenomena has been investigated by that one more, that is the Arbach energy and the subsequent years after next years, and identified as that Arbach tail or something. So these states are usually described by exponential function, that is e power like that exponential function, where corresponding to the distribution of density of state. So that is given in that plot, tau plot. Okay. So this something the reference they are given here for 6 and 7 also. You go to refer like this. So similar plots I go to take it something here. See here. So this is one such plot. So now I go to show the one more plot. You please wait. I go to share that one more screen. Okay. Yeah. See you whether the plot is visible for you. Check. Please confirm.
Yes, sir.
Yes.
Visible.
Okay. See here, you go to take some the standard material. For example, that is the Princeton is a standard material, and there are different concentrations here. See here, that is 1 into 10 power 12, 5 into 10 power 12, 1 into 10 power 13. So like that, the different concentrations materials. Based on that, you go to take the band gap determination. So the standard material, your band gap is almost, see, this is from 2 to 3, in between 2 to 3 is there. So almost it will very close to 3. So roughly, and this is 2.9 or 9.5 something. So this is for standard material. See here, standard material. And the remaining material, the different concentrated material having the different tau plots here. See here, the different tau plots here. So this is carried by, say, and each and every one, you go to draw the linearity, they go to draw the straight lines, and they go to cut the x-axis at a different places. And these are all the band gap of the materials for a different concentration. That is 2.5 something or 2.7 or 2.8 or something. Okay, so this is the different plot. Okay, and the energy along the x-axis again, and the absorption along the y-axis. Okay, and you go to measure the different values. Understand? Yes. Say yes or no.
Yes, sir.
Yes. So this is the article. Yeah, please understand. This is the article. Okay. See. You see the title of the article. Check. Yes. See, is this visible for you or not?
Yes, sir.
Yes, sir, it's
Yes,
visible.
sir.
Yeah. See, the first two names are you identified? Huh?
Yes, sir.
Yes. So
sir.
this is myself and my colleague. I think this Dr. Bhagiraj is one of my colleague. So he carried out this work, and I got to take both of you take this article where in 2017. I think almost this is acceptable in 2017. It is available online also. You go and check. This is 2017. Thin solid films. That is the name of the journal. Okay. So in the journal only you go to publish these results, and they go to measure the optical band gap of cadmium sulfate thin films that induced by that aluminum, that is Au9 plus gold, Au9 plus ion irradiation, like that. Okay, where they are using for optoelectronic applications. Okay, so this is a published article. In this published article in that journal, so with the help of that, see the calculations here. Okay, by using the same only they go to calculate it. See the cadmium thin film. Again they go to take the same Lambert's and Beat's law only. See here the same whatever you discussed here. See alpha, and that alpha h nu, that is equal to a h nu minus eg whole power n by n. So here is 1 by n. I go to take the root. So simply I put n here. So same only you go to use. The different band gap values are there: 2.87, 2.77, 2.71, and 2.56. These are all the different band gaps, different optical band gaps. Okay, understand? Yes.
Yes,
Say yes or no more, then only you understand. Yeah. Yes.
Yes, sir.
Okay. So
Yes,
now we go. Okay. Anyway, I go to stop this one. So that is an article. There is a research article. That optical, how you go to determine the band gap by using that UV visible spectroscopy. So that is data collected from where? That UV visible spectroscopy. So similar to this one. Okay. Here there is only one plot is there. There is only one material, and there the different concentration materials are. That's why you get 3 or 4 tau plot. Each concentration you go to measure how that band gap is varied with respect to concentrations or something like that. You go to studies. Okay. Any doubts more here? Any doubts or anything else? Please. Yes. Same. Whether I understand this tau plot or not. Say next we move on to the next topic here. Okay. Is it okay for you?
Yes, sir.
Yes. So then up to this, that is a one topic. Then come to the luminescence. See the concept of photoluminescence. This is our next topic. And then this is the last topic in that module 5. Okay, sorry, module 4. Okay, the concept of photoluminescence, and that is a radiative and a non-radiative transitions here. What is the meaning of luminescence? I think you studied in the lower classes. Anyone? Please. Fluorescence, luminescence, photoluminescence. I think whether you refer these words in the lower classes or not. They are using.
Yes, sir.
Yes. Yes. I think in the 12th standard, that the wave optics, I think you studied these things. Yes.
Yes, sir.
Yes. Okay. So that is a luminescence. So now you will say what is a photo? Photo means I think photons.
Light.
Light. Yeah. Okay. The luminescence is nothing but the excess of energy. Okay. That is radiation. Especially that is a EM wave, electromagnetic radiation. So the luminescence is the electromagnetic radiation phenomena due to excess thermal radiation or at an incandescence physical system. So that's why they are mentioned given here. Okay. Okay. Just wait. The screen is visible. I think now it's fully visible. Okay. See. So these how these things have happened, like that you go to see more. That's all. See, with regard to the luminescent semiconductor, there are a number of transition takes place in between. That is a band to band or a band to excitation or interband transition, intraband transition. So all the transition happened for two conditions: whether E is less than or E is greater than that band gap. Okay. So now the electrons, for example, the incident photon is equal or beyond the energy gap. So definitely the electrons is excited from valence band to conduction band. There is no doubt. See here, it will excite the electrons from where? Valence band to conduction band through the band gap. And generation, for example, the generation, semiconductor generation, the recombination radiation from the electrons coming from excited to ground state. The two processes are there. So absorption also will happen when the electron is excited to certain higher energy level from the neutral acceptor energy level, and it can also transit to ionization of donor energy levels like that. So these phenomena நடக்குது. பண்ண முடியுமா? Observe பண்ண முடியுமா? Is it possible? Just wait more. பண்ண முடியும். 20 minutes இருக்கு. பட்டு பட்டுன்னு போயிட்டு வந்துருங்க. ஃபோன் பண்ணாரா? Okay. Yes. Sorry. See, these things, see, absorption will also happen when the electron is excited to higher energy level from where the neutral acceptor energy level, and the vice versa like that. The trapping levels or something, or impurity levels. Okay. So what is the concept here? The luminescency concept, which inspects the optical property of this luminescent semiconducting materials, especially your semiconducting materials, where there are three different conditions you go to take it here. Okay. So the photoluminescence, whether it is a destructive, nowadays the non-destructive technology is very, very important for the strong and the non-destructive technology. And you can estimate the composition of the compound as well as where by using the peak intensity of the photoluminescence spectra. So that is a similar to a ultraviolet visible UV visible spectroscopy. This photoluminescence is also one such aspects to measure. See here, we can estimate the compositions of compounds. That is, what much amount of composition is present in that compound. How? By using that peak intensity of the results of the spectra, the PL spectra, photoluminescence spectra. That is one of the characterization technique. Photoluminescence is also one of the characterization technique. By using this, we can investigate where the internal interface of heterostructure and the general physical or electronic measurements of, okay, because it's not exactly measured, but this heterostructure is easily identified by using this PL spectrum, photoluminescence spectrum. But there are three conditions are there. What are the conditions? You go to see heat here. Listen, the process, the three procedure. One is the excitement. So that is excitation. Second, heat balance. Third is recombination. So excitation takes place when a photon of energy hν go to strike, or that is coming from where? That incident light. If the light energy go to strike, so definitely the electrons in the valence band gains the energy from these photons, go to excited state. If that energy of photon is far greater than energy gap Eg, that is E is greater than Eg, so definitely the excitement takes place, excitation. So the electron hole pair and recombines that to generate photons after heat balance. So that is balance, the transition, photon and phonon transitions here. So that impurities and defects from various energy levels in the band gap and their corresponding energy will generate the radiation by radiation recombination process. That is one type, or generate absorption by non-radiation recombination process. Are you understand this or not? Please. See, there are two types. More, it will generate. Yes.
Balance again.
See, there are two types. For one is the radiation recombination process or non-radiation recombination process. Okay, so the impurities, for example, already we discussed in that DLTS. So definitely there is no ideal crystal. Definitely the defects are there. Okay, so when you do this semiconductor is nothing but the doping of materials. So these impurities and defects from various energy levels, where in the band gap, in between the band gap, okay, that E and in between the Eg, so their corresponding energy will generate radiation by recombination process, radiative recombination process or non-radiative recombination process. There are two cases. One is radiative recombination, other one is non-radiative recombination. So radiative means definitely E is greater than Eg. There is no doubt. Non-radiative means E is less than Eg. That is the condition. So that condition already we discussed. Are you remember or not? I think in the third module, the first we go to see that module 3. I think the first two lectures you take a different carrier generation and recombination process. Please you go to check. Okay, understand?
Yes, sir.
Yes. Okay. The same is repeated here. See the next, the concept of photoluminescence. See again the same is repeated once again. Listen. So the luminescence of semiconductors again divided into two. One is radiative, other one is non-radiative. So when that is you say radiative and the electron, that the incident energy is greater than. See when the electron drops to the lower state from higher states, that is conduction valence band to conduction band. So it probably occur the radiative transition regardless of intrinsic state or the energy state formed by the impurities. So the system is not a balanceable condition, and we assume that the excited phenomena will generate that electron hole pair. So this is carrier generation process. Okay, so that is band to band transition or free carrier transition. There are so many cases are there, interband and intraband, and there are a number of. So all these things happened where in between the 3 to 5 compounds in the periodic table. So in the periodic table, the direct band gap material such as in between the 3 to 5 compounds where the electron hole pair will generate by radiation recombination process effectively between where the two bands, conduction bands and valence bands. Can you understand this? Say yes or no?
Yes, sir.
Yes, sir.
Yes. Okay. Now, again, what is the one more transitions here? See, again, the free carrier or excitation transition. So this is, for example, in the case of the pure material, electron and hole will attract each other to form that excitation. Again, that recombination takes place here in between the same 3 to 5 compounds, that is 3 to 5 compounds, and the free excitation energy is given by this equation here. See, and that is nothing but a normal equation, that is Zm square e power 4 by n square h square epsilon square, the same formula. So here instead of m, that m star is there, that is effective mass, E is the charge of electron, the remaining is same, h, Planck's constant, E that is a dielectric constant, and n that is a principal quantum number, n is the quantum number here. So this is the energy of the excited electrons, or excitation can be expressed by using this equation. Okay, so this is the free excitation transition, then again a free to bound transition. So that is a trapping mode. This is trapping. So based on this only they will give the problem one, and that problem I will go to explain. See, the transition is free to bound. Free to bound means in between the levels. For example, in between the valence band and conduction band, there are several impurities are there. That is bands are available. So the electrons coming from where? Jumping from valence band to that impurity, again that impurity to conduction. Similarly, the recombination takes place. Electrons come down from where? Conduction band to that impurity level, again it comes to valence level like this. So they're going to given here. So transition, free to bound transition between energy bands of the material and impurity energy levels. Impurity. So this transition is in between where? That impurity and one of the either conduction band or valence band, such as from conduction band to acceptor or a donor to valence band like that. And this difference, that Eg minus Eb is, that is Eb is you say bound energy for shallow impurity region. Then donor acceptor, based on the concentrations of donor and acceptor. So for example, if you get the D plus and the acceptor D or minus like that, and that the concentrations also varies. Okay, and the holes and electrons will bound at D plus and A minus locations to generate the neutral, that is a DO and AO centers. Some neutral donor electrons will recombine with the neutral acceptors also. That is also takes place. That is a donor acceptor pair. So all these things is a radiative process, photoluminescence process. The non-radiative is also there. So that is the next one. The non-radiative, some of the transitions, okay, which causes the non-radiative transition also where will compete with the radiative recombination transition, and that influence the luminescent efficiency negatively. One is the reason they are giving because of the thermal oscillation to generate photons, or the recombinations due to where the surface state that includes the two-dimensional dislocations or agglomeratory boundary and etc. And similarly, the impurity locations are often gives the non-radiative recombination centers, and this loss of energy, okay, for the trapped carriers will again generate the lattice and emitter non-radiative energy. Hello, sir, na class, sir, na. அவர் இன்னும் சொல்ல மாட்டார் சார். நான் கேட்குறேன். Okay, so listen. So this, the loss of energy where in the trapped charge carriers. Okay, so that also in the lattice form and it emit a non-radiative loss energy by augering process. I think this you studied in that module 3. Please remember that augering of electrons like that. Okay. So this is a non-radiative transition. So the concept of luminescence, you go to take these two things, whether it is radiative or non-radiative. Radiative means there are so many cases that E is greater than Eg, whether it is band to band or free carrier or free excitation like that. Non-radiative, that E is less than Eg. That is only case. The recombination process takes place here. Okay. Understand? Say yes or no?
Yes, sir.
So this, see, I think this is a last topic in that module here, module 4. And based on this, the problems, numericals will give at least 1 or 2. That is your lecture 16. You please wait. I go to share that screen also. Okay, that 1 or 2 problems are there. You just wait. I will show that one also. Yeah. So check the screen is visible for you. Yes.
Yes, sir.
Yes, sir, it's visible.
Yeah.
Yes,
Okay.
sir.
See, and the only one the problem, the 2 problems are there. Just now you discussed this one. See, for example, the gallium oxide semiconductor at 300 Kelvin temperature. See, the energy of the top of the valence band and the bottom of the conduction band is given. So that is 0.759 and 2.2. So what is the energy difference between these two? That is your energy gap. You understand? See, this is the top of the valence band and the bottom of the conduction band. The difference between these two gives Eg. That is your energy gap between valence band and conduction band. Okay. And if and the bound energy Eb is also given. So that is 0.6. So our aim is go to calculate what is the energy of the radiative photon. Energy of the radiative photon. So first you go to see what is Eg. So Eg is nothing but Ec minus Ev. So that is 2.2 minus 0.759. You get 1.441. So that is Eg. Then Eb is also given. That Eg minus Eb. See here? And Eg minus Eb is nothing but the energy of the radiative photon. So that is 0.841 eV. And you understand the problem here? Yes?
Yes, sir.
Yeah. So these type of problems they are asking for your exams. That MCQs also they go to ask. Simply one step answer. So that energy gap is given and EB is also given, but energy gap indirectly given. Instead of directly given the Eg value, they indirectly given and the top of the valence band and the bottom of the conduction band like that. So the difference is nothing but Eg here. Eg is nothing but Ec minus Ev. You go to substitute the values and find out what is. Sometimes that 1.441 directly given, you directly go to see what is the difference between Eg and Eb. That is your energy of the radiative photon. So this is one such problem related to the topic, and one more is that formula. Okay, free carrier transition. So you go to calculate what much amount of energy for the excitation in 3 to 5. That is aluminum oxide material. So effective mass is given. The effective mass is 0.1 times of the rest mass of electrons, and the quantum number is also given. N is equal to 1. So now you go to substitute the values and find out what is En like that. That's all. So 2 pi already you know. M star value is given. Okay, that is 0.1 times of M naught. E, charge of electron, you know, H Planck's constant. And dielectric constant is not given, means you say relative permittivity, that is equal to 1. And N is also given. Substitute all the values and find out what is E. That's all. Okay. Yes?
Okay, sir.
Are you understand this or not? Please. See whether I understand or not.
Yes, sir.
Okay. I think the only these 2 problems are related to these topics here. Okay, previously that ultraviolet visible spectroscopy, that is full theoretical concept and that is too difficult to understand for you. Okay, so there's no problem related to that one. So only the problem related to this one they are giving the photoluminescence. Out of that lecture number 14, 15, 16. So only the 16th, this is the 16th one, problems related to these topics. That's all. So similar problems, you go to work it out yourself. That's all. Okay. So any doubts are here? Any doubts or any clarifications, please? Anything else? Any doubts? Say yes or no more. Any doubts or clarifications, please?
No, sir.
Okay. What about others here? Simply the no one is
No doubt, sir.
No, sir.
okay.